Kyle Johnson here, and I just wanted to go over with you a little model, a double napped cone, so to speak, modeling what my article was trying to convey. So, without any further delay, let me turn that music down just a little bit. Hey, teenagers, cut that out! Well, I do have a heart. Anyway, what this basically models is that you've got a double napped cone, and I know it doesn't look like a cone because I can't draw in 3D. But anyway, right here in the center is where the atom is, and I call that the quantum event horizon, where things change, because this is really basically a model that simply shows the delta or change in complexity slash improbability. And so you start down here at the bottom, and there's arrows that point up and through this bottom cone, and then up through this inverted cone. So what we have here is we start down here at the bottom with an organism which is astonishingly complex and improbable for that matter. But then when you break that down into these more manageable parts, such as organ, tissue, cell, organelle, and molecule, you start to see the light of day and feel like you're catching on to things. But then we get to the atom, and that's where I ask, where do we draw the line, guys? I mean, I know Darwin used the word organ as the instrument of something that could possibly come up and interfere or challenge his theory. But, then where do we draw the line at organ? What if there was a tissue that could be shown to not create or destroy itself? What if there could be a cell or molecule? Well, we know that's not true. We know that clear down to the molecule. When we get to the atom, something changes. We see that the probability and the complexity decreases as you go up in this smaller cone. And then when you get to the atom and you begin to break down the atom, the improbability and the complexity begins to increase vastly. And that's basically all this model is. I mean, right here is the quantum event horizon, where, below that we can sum all of this stuff up to explain rationally the complex, improbable event of an organism. We can sum up the organ, which is a little less complex. It's still complex, but it's manageably so. And we can sum up the tissue, the cell, just like the calculus student does when they want to try to figure out the area or the perimeter of some kind of a complex irregular shape. We can do that here. Clear up to the molecule, summing all these things up to equal this highly improbable, complex organism. But when we get to the atom, which makes up the molecule, something happens. We begin to break that down. We break the molecule down and it's no big deal. We see the atom. It's all coming to us now. But when we start breaking down this atom, we're needing things like quantum mechanics. We've got subatomic particles. It's a new math that goes beyond Newtonian mathematics. It doesn't cancel out mathematics, but you can't apply Newtonian math to. It would be absurd to apply that to quantum reality. Well, then you get to superstring theory and M theory, and we're talking about developing an entirely new math language that's going to make quantum mechanics look pretty simple, actually. But it doesn't mean that we disregard Darwin's theory. It just means that maybe we need another volume to it, a volume like, instead, cosmological evolution. Seriously, a systematic volume, just like Darwin's systematic volume on the origin of species and evolution by natural selection. But this is Kyle Johnson, and I just wanted you to kind of see what was going on inside of my sloppy, messy head. Reporting to you from humble Wichita, Kansas. Hope you enjoy this article.